All right, this lesson is on the second half of the section on vector functions that talks about derivatives and integrals of vector functions. And really what we're going to see here is largely just a lot of background information that will allow us to do more interesting things in later chapters. But nonetheless, it's worth going over and making sure we understand these basic things, and we'll do some examples along the way. So the first result is if the function r of t is really just three functions, each multiplied by unit vectors I, j, and k, x of t I hat plus y of t j hat plus z of t k hat, then the derivative has exactly the same definition as for an ordinary function. If r is a vector function, the derivative is still the limit as delta t goes to 0, r of t plus delta t minus r of t divided by delta t. When we break that down into its components, we have the x functions, x of t plus delta t minus x of t, both times I hat. Multiplying j hat, we have y of t plus delta t minus y of t, and multiplying k hat, we have z of t plus delta t minus z of t. So when we break this limit down into its components, we have now simply the limit of scalar functions, which we see to be exactly the definition of the derivative of these scalar functions, each multiplied by its respective unit vector. And so what we get is just the derivative of each of the three scalar component magnitudes, x prime of t, y prime of t, and z prime of t, multiplied by the unit vectors, and we call that result either dr dt or r prime of t as indicated here. So all you do is you take a vector function, you differentiate it component by component, at least in Cartesian coordinates. Now, we've seen in other places in earlier sections that the derivative allows us to construct linear approximations, and that what these linear approximations correspond to are the 0th and first terms of a Taylor series. So that's true in 1D. We have an expression for y in the vicinity of some point x naught comma y naught. The 1D approximation of the function is given by the first two terms, y naught plus dy dx times x minus x naught. And with the definition of a derivative, that remains true for vector functions. So the vector function r is approximately r0 plus dr dt times t minus t0. Now we see this right here to be the equation for a line, exactly the equation for a line. And what kind of line is this? Well, if we look at the limit that we have, it's the limit as delta t goes to 0. It is just like in Calculus 1, a limit of secant lines. If we have, say, here a point t naught, and we now examine delta t's of various sizes, then we obtain first this secant line, and then as delta t gets smaller, we obtain the orange secant line, and as delta t gets smaller still, we obtain the yellow secant line, the green secant line, and so on. And we see that in the limit, this is equal to a construction of a tangent line. So because the derivative of a 1D function, of a vector function, ultimately gives us a tangent line, it gives us the direction of a tangent line, we call r prime of t a tangent vector. It is a vector that starts on the curve and points off in the direction of the tangent line, and we call it a tangent vector. So that's an important geometrical fact to know about the derivative of a vector function. It's very often useful to consider not just the tangent obtained by the derivative, but to construct something called a unit tangent. And the unit tangent is simply the derivative of the vector function, which is a tangent, divided by its own magnitude, which we see here. And that gives us a unit tangent. That unit tangent is a function of the parameter t. As t moves along the curve, then the unit tangent changes direction. But what's nice about the unit tangent is that it is intrinsic to the curve itself. If you imagine different parameterizations of a curve, which, say, move along the curve more or less rapidly with respect to the parameter t, then the derivative of the vector function will be larger or smaller, depending on how rapidly t moves along the curve. In some sense, you could say, well, that's fine, but I don't really care about your parameterization. If I'm talking about the curve itself, I want to know just which direction is the curve pointing. And so the unit tangent gives us that information, the direction of the curve, without having any dependence on the rate at which that particular parameterization is moving along the curve. So it's a nice handy sort of intrinsic geometric object that is useful to be calculated frequently. So for example, let's do our first example. Let's take a curve. Here's a parametric curve, x equals cosine t, y equals 2 sine t, and let's compute the unit tangent of that curve. We have the ordinary tangent, r prime of t, given by this simple formula. We just differentiate x and y component by component. So the derivative of cosine is negative sine, the derivative of sine is cosine, and so we get negative sine and 2 cosine of t. Then we calculate the magnitude of that vector, which is obtained by squaring both components and taking the square root. It's the square root of the dot product of r dot times itself. So we get sine squared plus 4 cosine squared of t. This is a mistake, I'm sorry. It does not actually equal this square root of 5 here. That was an earlier mistake that I made. Instead, it equals negative sine ti plus 2 cosine tj, simply divided by this square root. Obviously, since these are not the same number of sine squared and cosine squared, they don't turn into a constant. So apologize for that. Here's a sketch of the situation. We have here, sorry about that. We have here an ellipse. We hopefully recognize this curve as the parametric representation of an ellipse with width in the x direction 1 and height in the y direction 2. And as this t traverses the ellipse, the unit tangents simply point in different directions as t changes. So there is that. Okay, so unit tangent. Unit tangent is probably the most important thing that you need to know about curves, vector functions, describing curves. But there's a little bit more technical stuff that we need to cover in this section. So first, definition of smoothness of a curve, continuity, differentiability of vector functions, and so on. So just like in plain old one-dimensional functions y equals f of x, a vector function is called continuous on some domain if, for every point in that domain, the value of the function exists, its limit exists, and the value equals the limit. So for instance, let's see, I've been having trouble with my pen here. But for instance, if we have, say, a function that moves along and then it's broken and it goes somewhere else like this, that would be a discontinuous function. If we have instead, again, one of these tricky functions that is kind of shown in calculus where you have a function that, really sorry here, that moves along and is not quite defined at one point and has some other value at that point. This is one of these ridiculous functions that's only invented to make pictures in a calculus textbook. This would also be discontinuous at this point. But if the curve is connected all the way through from a point t equals a to this corresponding point associated with t equals b, we call it continuous. Similarly, a vector function is called differentiable if the derivative function, r prime of t, is continuous, and so on. So the second derivative is twice differentiable if the second derivative is continuous, and so on. So that's all fine. That's the same definitions as in Calculus 1, but what are the implications for parametric curves? So as was the case in Calculus 1, if y equals f of x, then if it's continuous, that means it's connected. So that definition doesn't change. If it's continuous, it's connected. In Calculus 1, differentiable basically meant smooth. However, there's an extra catch. We'll show this with an example, but in order to call a curve smooth, we actually now have, for a vector function, two requirements. We require that r of t is differentiable, and that r prime of t does not equal 0 anywhere on the curve, the section of curve, within that parameterization. So, and if we have a curve that is not smooth at some point, but smooth everywhere else, then we call the whole curve piecewise smooth. We'll do an example to illustrate these terms. So here's our example. We have t cubed I and t squared j. That looks like a nice, simple vector function with just algebraic terms multiplying I and j. And indeed, we take the derivative function r prime of t, we get 3t squared I and 2tj. That looks nice and continuous. So indeed, the function is differentiable. R prime of t is continuous everywhere. and so the function is differentiable. But we should notice that r prime of 0, when t equals 0, both of these vanish, and r prime of 0 is 0. And so what's the big deal? Why does that happen? Well, let's investigate more closely. If we eliminate the parameter in this parametric representation, we say x equals t cubed from up here, then we could say t equals x to the 1/3, and we could then plug that back into the expression for y and get y equals x to the 2/3. And that function looks like this. Comes in, negative values of x, and then it has a cusp at the origin and goes back off, slowly increasing for positive values of x. And so what basically happened here is that as t approached 0, the rate at which the curve was being generated with t vanished. It slowed down as t increased. It's moving quickly. As t increases closer to 0, it slows down, slows down, slows down, slows down. And there's a moment when the curve basically stops. And in that moment, it changes direction, and then it continues off in some other direction. So even though this curve is continuous, and even though the derivative is continuous as well, the vector function is differentiable, but the curve is not smooth at that point because r prime of 0 vanishes. So the whole curve, we say, is only piecewise smooth. That just means that this piece is smooth and this piece is smooth, but the whole curve itself cannot be called smooth because it has this cusp. And that's the basics of curves, differentiability of curves, and what it means. A couple more things. So we have vector functions, and we can do things like multiply them by things, multiply them by other functions, take dot products of vector functions, and we might want to consider taking derivatives of these kinds of things. So what does it mean when we take the derivatives of products associated with vector functions? First, vector functions are linear, so we can take any linear combination of functions, some constant times r1 plus another constant times r2, as many as we want, and we can basically bring out those additions and scalar multiplications outside the derivative and simply operate on each of the vector functions by itself. So r prime 1 of t, r prime 2 of t, we can just do those one at a time and then put the pieces back together and get the correct result. And that's the definition of linearity, that you can take something like this and break it apart into pieces, take the derivatives of each piece, and put them back together. Now that only holds for scalar multiplication and addition, but those are two important operations, and it's very convenient to be able to take differentiation out of those operations. If we have, instead of a scalar multiplication, a constant multiplication, and then we have some scalar function times our vector, that still is a vector. When we take the derivative of that, we just apply the product rule exactly like you might expect. F prime times r of t plus f of t r prime of t. It's exactly what you'd expect, except this r has an arrow over it. Similarly for the dot product and the cross product of two vector functions. It's exactly equal to the product rule as you would have seen in Calculus 1. Last page. On integrals, and this is again, just as we saw for derivatives, taking the derivative of a vector function was very simple. You just took the derivative of each piece on its own. It's exactly the same for integrals. So r of t is nothing more than x of ti, y of tj, z of t times k, and we can then do those integrals separately because integration is also a linear operation, and here we're just multiplying by a constant unit vector. So we can do the x integral, the y integral, the z integral all separately, and then put the results back into the vector, and we have what's the integral of the vector function. Again, similar to Calculus 1, we say that a function capital R is an antiderivative of little r if capital R prime equals little r. And with that notation, we now can express the fundamental theorem of calculus for vector functions. And so it's exactly the same. The derivative of some integral from a to t of r of tau d tau, the derivative of an integral is the function, the original function, and the integral of the derivative of the antiderivative, that's kind of confusing, but the integral of the derivative of r prime can be expressed just in terms of r at the boundaries b and a. So this is just the fundamental theorem of calculus expressed for vector functions. So for example, very simple example to conclude the video, we have some random vector function, t tangent of t, ln of t, and we can integrate those piece by piece, and this is just an exercise in some Cal 1. T becomes 1/2 t squared, integral of tangent becomes negative log of cosine, and the integral of ln of t is t ln of t minus t. And if you don't remember how to do these Cal 1 integrals, this would be a good time to go remind yourself.